Right, equilibrium. So it's all about reactions which are reversible. In other words, our reactants can form products, and our products can also go back to being reactants. So some reactions you've maybe come across, like burning magnesium, that's clearly just going to be one way. It's very hard to go back from magnesium oxide to magnesium and oxygen, but other reactions are reversible, and we're going to learn about those reversible reactions and what we call equilibrium constants and reaction quotients, and look at what factors affect the position of equilibrium, like where is that balance as well in our equation. So this is defining equilibrium, and where we're at a point of equilibrium, we can say our rate of the forward reaction, in other words the rate of that change, is equal to the rate of that. So there's stuff still going on. These are still reacting to form this. This is dissociating back to these. But because they're happening at the same rate, you can see there, that's our position of equilibrium, we're not seeing any change in the concentrations. There's no net change in the concentrations. They're appearing to be fixed. They're constant. We can also see equilibria in physical systems. So if we take just a conical flask with some water in it, stopper it so it's closed, then some of our higher energy particles are going to be able to escape the liquid phase and form a vapor. And there we can see there's our vapor formed. And some of those vapor particles are going to condense back into the liquid phase, and what we've got is an equilibrium between our liquid and our vapor. Now, the amount of particles that are going up into the vapor will depend upon the intermolecular forces. So if something's got very, very strong intermolecular forces, fewer particles are going to be going off up to form a vapor. If something's got weak intermolecular forces, it's easier for the particles to form a vapor. And we can assign an enthalpy of vaporization to a substance, like the amount of energy needed to vaporize a mole of the liquid to become vapor. So hopefully you can understand as well that temperature is going to play a very significant part in this. So if we heat this up, more of the particles have enough energy to overcome their intermolecular forces and form a vapor. As a result, the vapor pressure increases. So if we were to plot on here something that had stronger intermolecular forces, so let's say that this is, I don't know, methane, and let's say we're doing, that's not a very good example, let's choose methanol, it's a liquid, right? And then let's consider what the curve would look like if we had ethanol, which is a little bit bigger, which means it has slightly stronger intermolecular forces. What we'd find is that at any particular temperature, we're going to have slightly less vapor being produced because the particles are less likely to be escaping into that gas phase. Now we can write equilibrium expressions to show what's happening in these chemical equilibria. So there's the first thing to note, is that your chemical equilibria will have this symbol in it. And so our equilibrium constant, which talks about the position of the equilibrium. So equilibrium constant, given the symbol Kc, and we're going to be dealing with things that are either gases or aqueous solutions in this unit. We're not probably going to come across any heterogeneous equilibria, although I notice there is an example of one creeping in here. What we're doing is putting our reactants over our products, our products over the reactants, and raising them to the coefficient that they are in the equation. That's how we're going to write an equilibrium constant. So let's focus on this example, because this is a heterogeneous equilibrium, and for the heterogeneous one we'd be looking to leave that out of our expression. We don't really want to go into that here. So we'll just focus on this one, and you can see I've got my NH3 raised to the power 2, H2 cubed, N2 there as well. Square brackets referring to kind of concentrations, and our units of Kc will change depending on what's in our expression here, because each of these, the square brackets imply mole per decimeter cubed. if I work out moles per decimeter cubed times moles per decimeter cubed divided by moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed times, things cancel down to that, right? So the units for Kc are going to vary depending on what is in this section. Now Kc is useful because it tells us where our equilibrium lies. Right? If Kc is much bigger than 1, you can imagine that means that this number here is significantly larger than these. It means my equilibrium is well over to that side. I've got mostly products. If it's much less than 1, then it would mean that that's a small number. These must be bigger. It means my equilibrium is still mostly over at the reactant side. Now, we can play around with these Kc values a little bit. So here's a pretend reaction. And so that's the Kc expression. You can see the substances raised to the powers. That's products over reactants. Now, if I was to look at the reverse reaction, in other words, if I was to do C plus D in equilibrium with A plus B, then hopefully you can see, and you can prove this for yourself, that my Kc would be this times this over this times this, which is in other words the inverse of that. So my new Kc, you can see there, is 1 over Kc. If I'm doing multiples of this, let's say I'm doing twice all of this, then you can imagine that I've got a 2 creeping in up here, and I've got a squaring effect. If I'm doing halving all my coefficients, then I've got these being raised to a half, and something being raised to a half is the same as square rooting it. If I'm adding in another equation, let's say I've got this equilibrium that I want to add into it, then my new equation would become WA plus XB plus N in equilibrium with YC plus ZD plus M. Then my equilibrium expression becomes C to the Y times D to the Z times M over A to the W times B to the X multiplied by N. And so for this individual thing here, that would have been M over N. Hopefully you can see that this is therefore just the product of the two separate equilibrium constants. So you can prove all of these relationships when you come to manipulate Kc values. Now the reaction quotient indicates how a reaction is going to change if it's not already at equilibrium. Right, so how is it going to move to achieve equilibrium? So if Q is equal to K, then it's already at equilibrium, we're not going to see any changes. But if Q is less than K, if the value of Q, which is going to be worked out by the same kind of method, turns out to be less than K, it's going to have to shift because it's going to move eventually to get to that equilibrium Kc situation. So you can see an example down here. If we work out Q for this to sort of find out where it's at, then we can do Q is equal to same setup of sum, so it's going to be concentration of that multiplied by concentration of that raised to its power divided by concentration of that to its power. Work that out. Comes out to be 3.38. And if we look, we're then in this situation here where our Q value is bigger than the Kc, and so we're going to see the equilibrium shift to the left. It's going to move towards the reactants like that. Now, Le Chatelier's principle is very important in kind of describing and explaining how changes to a system will affect the equilibrium. And essentially, the equilibrium is going to move to try and oppose any change that you make to it. So something that's at equilibrium will shift to oppose any change that you make to it. So you can have a read through those. If we look at this example down here, it says what conditions will maximize the yield of sulfur trioxide. So if we think of pressure first off, on this side of my equation I've got 3 moles of gas, and on this side of the equation I've got 2 moles. So if I have a higher pressure, the system's going to try and relieve that. It's going to try and reduce the pressure, and it's going to be able to do that by moving to the side where there are fewer moles of gas. So if you've got less moles of gas in your container, you've got less pressure, right? There's fewer collisions with the side. So if I have a higher pressure, then I'm going to see my equilibrium shift to the sides where there's fewer moles, the lower pressure side. So one of the things I'd be looking for is a higher pressure. So a nice high pressure, and I'm going to see this shift this way, and I should then end up with more of my sulfur trioxide. In terms of temperature, that delta H is referring to that direction. So moving in that direction is exothermic. So we need a low temperature, right? That's going to encourage it to move in its exothermic direction. So a low temperature means that your reaction is going to try and heat things back up again, and it can heat things back up, can release heat by moving in its exothermic direction. So we're looking at having a low temperature. Now we might not run at a super low temperature in reality, because if we have a low temperature we're also going to see a rather slow reaction, right? So we sometimes have to consider the balance between a good yield and the rate of the reaction, but a low temperature would give us a higher yield. Other things we can do, we can add in maybe some more sulfur dioxide. The reaction is going to try and use that up, which means it's going to be shifting to the right more. Or we could be removing this as it's produced, because again, as soon as that's removed, my equilibrium shifts to replace it. Right? So we can either add in more reactants, or we can remove the products as they are produced. All of those will give us a better yield in industry for that sulfur trioxide. Now, the only thing that's going to affect the value of Kc, so Kc is an equilibrium constant. You'll maybe notice in the questions above it's always been quoted with a temperature, and it's because Kc, the value of Kc, is affected by temperature. So if we look back at this example here, then as we get this equilibrium to shift by changing the temperature, then we would see a change in the value of Kc. So this lower temperature where our equilibrium is shifting over this way, we're getting more of this stuff. We would expect to see, if we write our Kc expression, SO3 squared over SO2, it's not fitting in, O2, we would expect to see more of that there. Therefore, we see a larger Kc. So the only thing that affects the value of Kc is temperature. With the other examples, Kc is staying constant, and we're seeing the equilibrium shifts to accommodate Kc staying constant. But temperature will affect the value of Kc. Catalysts don't affect values of Kc, don't affect positions of equilibrium. What we're seeing with a catalyst is that our rate of forward and the rate of reverse reaction, so if that's our energy profile and then we add the catalyst in, it maybe looks something like that, you can see that both the forward and reverse reactions have benefited in terms of lower activation energies. Yeah, if our original activation energies were all the way to that, both have benefited, so both the forward and reverse reactions are faster, and we just reach equilibrium quicker. We don't see the position of equilibrium change. Here's another example. You can have a look at this. You can see what the effect of lowering the temperature is and what happens if we change these conditions, remembering of course that Kc values will change with temperature, but everything else will not affect the value of Kc. That's what we've covered. There we go.